Hi, I'm Michael Alvarez, a professor of political and computational social science at Caltech, and I'm super excited today to hear from my colleagues, Sara Kangaslahti and Danny Ebanks. They're here to talk about a new publication that's forthcoming in political analysis. Danny and Sara will start by discussing the big picture. Then Sara will focus on the methods and theory. Danny's going to close out the conversation by connecting the research to applied political science work. And then Sara's going to tell us a little bit about how you can access the code and package to run this application on your own. So over to you, Danny and Sara.
Great. Thanks, Mike, for that kind introduction. We're really excited to talk about this new research. So the title of the paper, of course, is Analyzing Political Text at Scale with Online Tensor LDA. This is with our excellent co-authors, of course, three of us on the call today, and John Kasafi and Anima Arankumar, who are both at NVIDIA, and John is at NVIDIA, and Anima is at Caltech. Okay, so we want to zoom out and talk first about the big picture. So, topic modeling is an eminently popular method for natural language processing in not only in political science but across the social sciences. Um, Now, standard approaches to sort of the classification tasks and other sorts of goals that folks have with unstructured data, of course, are to use some of these unsupervised topic modeling methods. Of course, now LLMs have become very popular. In the past, folks have used embedding methods in order to better understand the text and better to understand the sort of latent structures that exist inside of them. Now, within social sciences, topic models, of course, are quite richly studied. Um, with sort of derivations thereof. So there's of course latent Dirichlet allocation, there's structural topic modeling, and many comparable methods, topic model-like methods that have been, at the forefront of a lot of the classification tasks in unstructured data. Now, the goal, of course, in many of these tasks is to extract the important information without requiring hand labeling, which of course is both is extraordinarily resource intensive, both in terms of having to require hiring many labelers, and of course, it's quite expensive. So this is resource intensive in terms of the sort of actual effort involved. And of course, it's not scalable, right? So for the large number of texts and large number of documents that are becoming more and more common in all sorts of applications, these are just not feasible methods to employ at scale. And in fact, it's been found in the empirical literature that intercoder reliability is essentially bounded at zero point 0.7 for many of these classification tasks. So even sort of with the most sophisticated resources, with the sort of highest quality annotators, the, the task itself, has certain bounds. So, of course, we're living in the world of large language models, and I want to turn it over now to Sarah to talk a little bit about where that might leave us.
Yeah. So LLMs have become very popular for a variety of downstream applications, including some of these topic modeling approaches. But there's a lot of issues with just using these LLMs out of the box. Specifically, a lot of these large models are proprietary. And also there's issues with the black box nature of these models. So there's limited understanding of why they're making certain predictions. This also makes replication of LLM results difficult. And pre-trained models may not necessarily respond very well to these applications such as social media, where the vocabulary and context can change rapidly. So you may need to do additional fine-tuning or prompt engineering in order to apply it to these rapidly changing contexts. Yeah, it's also necessary to like further understand the labels generated by the LLM because they may not have the same sort of conceptual clarity as some of these unsupervised approaches. However, a lot of the existing LDA methods have a lot of limitations that make it hard to apply them at scale. Specifically, there's poor posterior inference, where a lot of errors compound. So the law of large numbers doesn't apply in this setting. Also, they face a lot of memory and compute constraints because they rely on this variational inference or Gibbs sampling-based approaches. This causes slow convergence, and it can take weeks to months to run a single run on these large-scale datasets. This makes it really challenging to use these methods in practice, especially because these unsupervised approaches need to be tuned in order to validate and check for the robustness of the model. So we instead propose a scalable tensor LDA approach, where instead of using these variational inference or Gibbs sampling-based approaches, we instead expand on the literature of tensor-based methods, where we decompose the third-order word co-occurrence matrix. However, a lot of the existing approaches required explicitly constructing these second and third order moments, which is very computational and very expensive in terms of computational and memory resources. And so what we propose is a centered approach that allows for much simpler computations of the second and third order terms, since we don't need to compute these co-occurrence terms, or these cross terms, which make the computation of these second and third order moments much more expensive. This allows for us to have this fully online pipeline where we can have a single batch of data and update the first, second, and third order moments. And then we can directly extract the topics from these factorized third order moments. This allows for a scalable pipeline that can be implemented end to end on GPU. And this allows for an approach that adapts to data that's coming online.
Great. Awesome. Thank you so much, Sarah. I think that's a really great short summary of the method and some of the computational benefits. And I want to talk a little bit now about why empirical research needs these innovations at scale. So we hinted at it at the beginning of when we first started this talk, but there's been an explosion in new, large, rich text data sets. And this is a really exciting time in empirical social science because this explosion in data allows us to answer new, existing, long-standing questions, and also ones that we've never even thought of before. So questions related to sort of timeless concepts such as agenda setting, polarization, how responsive policymakers are to certain changes in public opinion, how representative, new forms of measures and forms of representation, how are our political leaders, are they mimicking, are they mirroring the messaging that we're seeing among our online publics? We can think about and study the spread of misinformation or voter preferences and all kinds of multidimensional data that are just new and exciting and really have opened up an entirely novel frontier of research. Now, what's really important here, and I think methodologically speaking, what's important is that this scaling can actually democratize some of these methods. So the idea here being that if we have feasible estimation, if we can actually run some of these methods on the sort of GPUs like consumer grade GPUs, this allows for more feasible robustness checks. That is, when estimation becomes feasible, we can of course sense the sensitivity of our models to our assumptions. We can do more hyperparameter testing. We can see if different sets of hyper and tuning parameters lead to different outcome solutions. Of course, this is great because then we can say, well, we trust these results or we do not based on those sort of robustness checks. And so as Sarah was saying, we proposed a fully online GPU-based tensor LDA method. This allows us to have a streaming version of the software, a streaming version of the method, and of course it runs end-to-end on GPU, which is unique. So from the pre-processing to the loading of the data, to the cleaning of the data, and finally to the model estimation and inference can all happen all at once on the same chip. This, of course, removes lots of latencies. You're not reading and writing across disk. Everything can be loaded into memory, and it runs in a nice streaming way. This, of course, allows for real-time inference, right? So unlike other methods, we can, of course, do inference in truly real time. As the data come in, we're able to actually report on and calculate certain measures that would be of interest to both researchers, policymakers, and the public abroad, at large. The way we're able to do this, of course, is, as Sara said, is by achieving optimal scalability, essentially by centering and batching the data. So through some clever algebraic manipulations, we're able to back out a method, a tensor LDA method, that has theoretical guarantees of accuracy. And this is the important point, that unlike some of these other methods we've talked about, this particular method has theoretical guarantees. And so that gives us a little more heft when we're doing our inference. That is to say, our method actually is backed and is provably accurate, right? It has nice bounds on accuracy, it has nice large sample properties, and we're able to back out those same parameter estimates, which have all those great guarantees, under this new approach, and at the same time achieve optimal scaling. And so we're going to talk a little bit towards the end here. We'll talk about the end-to-end GPU pipeline that's available in the Tensorly suite of packages. But first, I want to basically talk a little bit about our takeaways. So in this particular method, we've proposed a scalable tensor LDA method for large data sets that goes end-to-end on GPU. It's 100 times faster than the best off-the-shelf methods, and there are gains in coherence, accuracy, and in synthetic experiments. We think we can have completely new findings because we're able to report results on a full population of text, not just samples that we're doing inference on out of sample. And it resolves some of the tension with problems imposed by high dimensionality, such as the computational problems and the computational costs and the labeling costs. We've uncovered, in this particular paper, we actually report on two very timely topical areas. Of course, one is on the Me Too movement, and the other is on COVID discourse. These are both social media analyses with millions and tens of millions of tweets in which we process and label through our method. And we were basically able to uncover an analysis about the ephemeral nature of political topics. So, of course, while these topics themselves are political, embedded in these these are also cultural touchstones, historical touchstones. Embedded in them are these political dynamics, and we show how there's an ephemerality to them, that they sort of phase in and phase out. And the second is that there's a persistence in all of these on the personal. So we find strong evidence that through this method, that the way users on social media engage with these very prominent, nationally relevant topics is through the use of personal stories. And so in terms of future work, I want to turn it back over to Sara just to talk a little bit about basically three pieces of work that we're working on actively, both jointly and with our team of co-authors here.
Yeah, so we are working on these innovations in a variety of different settings. The first is combining this approach and extending it to the tensor joint sentiment topic models and improving on variational inference for topic modeling. We're also interested in new applications such as agenda setting and congressional party leadership, particularly this data set of congressional speeches from 1877 to 2015. We're also interested in using this approach to create inputs for frontier language models. So combining the topics we get from this tensor LDA method in order to, with language models, in order to develop better topic modeling approaches that can leverage some of the linguistic information embedded in these language models.
Great. And I'll just close it up by saying the software is available on Tensorly, which is a suite of packages in Python. And you can basically use, I believe it's a scikit-learn, kind of the scikit-learn syntax to go and run your models, and it should be very familiar and feel very friendly, and it's available now.
Well, great. Thank you both for being here today. This is a really exciting paper that represents actually years of work, in particular by the two of you and Jean. And we're very happy that this paper is now forthcoming in political analysis, and that there is a preprint version of this paper that is available as we release this video. I'd like to point out again that folks can go to the URL at the bottom of the screen here and explore how to use this provable natural language processing tool to process and analyze very, very large text data sets very rapidly. So again, Sara, Danny, thank you for being here today.
Thank you, Mike.
Thank you, Mike.